Welcome back to lesson 110 on mathematical modeling and variation. In the last video, we talked about direct variation, and we got through some information on direct variation as an nth power, but we didn't get to the example, so let's do that. Example 4. This is going to be the distance. A ball rolls down an inclined plane is directly proportional to the square of the time it rolls. And during the first second, the ball rolled 8 feet. We have to do two things. First, we need to write an equation relating the distance traveled to the time. And then we have to determine how far does the ball roll during the first 3 seconds. So let's start with part A. Let's write that equation. So there is some information we know. We do know that the distance, which let's just call d distance, it varies, or it is directly proportional. So we know d is equal to the square of the time it rolls. So we're still going to use k for that constant of variation, but let's use t for the time, and since it's proportional to the square of the time, we're going to square t. So we actually have our equation generally down, but it's not the equation that represents this exact situation. We have to figure out k. There is some other information we know. We do know that it traveled 8 feet, so d is going to equal 8 in the first second. So let's let t equal 1. 1 squared is 1, and if we divide both sides by 1, we're going to find that k is equal to 8. So we're going to take this 8 and put it into our equation that we have started. So our equation for this situation is d is equal to 8t squared. That is our answer for part A. Let's look at part B, where we are wondering how far does the ball roll in the first 3 seconds. Well, all we're going to do is we're going to replace t with 3. So d is equal to 8 times 3 squared. And we know 3 squared is 9, so we have 8 times 9, and 8 times 9 is 72. So that means in the first 3 seconds, the ball travels 72 feet. Let's look at inverse variations next. So an inverse variation. So there are 3 statements that are true. So the following statements are all equivalent. So first, y varies inversely as x. The second equivalent statement is y is inversely proportional to x. And our final equivalent statement is y is equal to k divided by x for some non-zero constant k. And this can also be true if we had an nth power. So let's look at an example. We'll call this one example 5. So here we're going to look at a company has found that the demand for one of its products varies inversely as the price of the product. When the price is $6.25, the demand is 400 units. We want to approximate the demand when the price is $5.75. So I'm first going to let D be the demand and P be the price. Because what we know is that the demand varies inversely as the price. So we can write this as D is equal to K over P. And we need to figure out K. What we do know is that D is 400 when P is 6.25. So we can write this as 400 is equal to K over 6.25. And what we can do to solve for K is we can multiply both sides by 6.25. What this is going to give us is K equaling 2,500, and we have now an equation that will relate price and demand. So we can go D equals 2,500 divided by P. So this is just an equation. This is not our final answer. We were asked to approximate the demand when the price is $5.75. So we're just going to replace P with that. So the demand is going to be 2,500 divided by 5.75, which is approximately 435 units. So if this company changes the price of their product to $5.75, they can expect the demand to be about 435 units. Let's look at an example where we could have both a direct and an inverse variation happening at the same time. So here we're in example 6. And we're looking at a gas law states the volume of an enclosed gas varies inversely as the pressure and directly as the temperature. The pressure of a gas is 0.75 kilograms per square centimeter, when the temperature is 294 Kelvin and the volume is 8,000 cubic centimeters. We need to A, write an equation relating the pressure, temperature, and volume, as well as in part B, we're going to find the pressure when the temperature is 300 Kelvin and the volume is 7,000 cubic centimeters. So part A, what we know is that the volume, which we're going to just use V to represent, it varies proportionally. So inversely as the pressure, so we're going to write K over P for pressure, and directly as the temperature. So let's just multiply K by T. And that's fine if we do this. Now, there are some values we know. We do know that the pressure is 0.75 when the temperature is 294 and the volume is 8,000. So we're going to take these three values and plug them in to the equation we have. So we have 8,000 is equal to K times 294 divided by 0.75. Now, to solve this, we can both multiply by 0.75 and divide by 294 at the same time. If we do this, what we'll find is that K is going to be about 1,000 over 49. And I'm not going to simplify that any further. So our equation we can write as V is equal to 1,000 over 49 times T over P. So part A, we're done with. Let's move on to part B. So in part B, what we want to do is find the pressure when the temperature is 300 Kelvin and the volume is 700 cubic centimeters. So, 7,000 cubic centimeters. Let's put in what we know. We know that the volume is 7,000. That's equal to 1,000 over 49 times 300 over P. Now, what I'm going to do first to get P by itself, I'm going to first isolate the stuff in the parentheses. So I'm going to multiply both sides by 49 over 1,000. That's going to get rid of that on the right side, and if I multiply that on the left, the 7,000 can simplify to just a 7. So we're going to have 49 times 7, which is equal to 343. So we're going to have 343 is equal to 300 over P. Now something we can also do, because we want to get P, we can multiply both sides by P. And what we're going to end up with then is just 343 times P is equal to 300. Now to get P by itself, we're going to divide by 343. And the pressure, if we go 300 divided by 343, is going to be about 0.87 kilograms per square centimeter. And we're done with example 6. We have one more thing to talk about. And what we can say is the statements below are equivalent. And first we can say Z varies jointly as X and Y. We can also say Z is jointly proportional to X and Y. And lastly, we can say Z is equal to KXY for some non-zero constant K. Example 7. We're going to look at the simple interest for an investment is jointly proportional to the time and the principal. And after 1 quarter, which is 3 months, the interest on a principal of $5,000 is $43.75. We need to A, write an equation relating the interest, principal, and time. And then B, find the interest after 3 quarters. So in part A, we can write a formula as the interest is equal to our K value times the principal times the time. But we don't know K. We do, however, know that the interest is $43.75. The principal is $5,000. And the time is 3 months, which as a fraction of a year is 1/4. So let's figure out what K is. If we were to multiply both sides by 4 and divide them by 5,000, that will get rid of everything on the right except for K. And it'll also help us figure out that K is about 0.035. So our equation is I equals 0.035 PT. Now we have to figure out, for part B, the interest after 3 quarters. Our principal is the same, so we're going to go 0.035 times 5,000. But this time we're not going to multiply by 1/4, we're multiplying by 3/4. Type it into a calculator and you'll get 131.25. That is our interest. And that wraps up Chapter 1. We're all done. We'll have a test sometime soon.